So fine, you're welcome once again to the last chapter or the last phase in the chapter about hydrodynamics, and this what we talk about surface tension. And under this slide, we are going to be talking about introduction and the significance of surface tension. Now, to understand the concept of surface tension, we can start with the definition, and we can write like surface tension, that for the sake of writing, surface tension is the intermolecular force that acts on the surface of a liquid and makes it loose like like an elastic membrane. I think that is better. Elastic membrane. So we are talking about another form of intermolecular forces. You know, I said forces of nature. We talk about intermolecular forces. There are different classifications of forces under mechanisms which we have discussed. But in this video, we are only going to be looking at the hydrodynamic as we're talking about forces, intermolecular forces. But here under surface tension, we are looking directly into forces acting only at the surface. And when the force acts only at the surface, they don't act under the surface. So those forces that act at the surface of the liquid and make it look like what it has been stretched. I hope you understand that that particular force is called the surface tension. Now, to understand this, we can quickly look at to get it very well, to know the significance and how it acts. We can just consider a box. I'm looking at a box. I think it should be better to have a good diagram, which I'm trying to do, guys. Just have to wait for some minutes. So we are going to look into a box, and inside that box, we are going to fill the box with liquid to a particular level. So we consider this box, as you can see, my dear student, looking at this box. Now we fill the box up with liquid to a particular level. Let's say the box is filled up with liquid up to to the highest level. So considering that, we can quickly do this for the sake of time. Just permit my diagram not drawn to scale. Now, this is a box or a cube, anyhow you want to call this, which is filled with water. You just have to take it slow and steady. Now, when we talk about forces that act on top of this, I'm going to change the color for us to see it now. We only want to consider the surface. And if we want to consider the surface, we are going to take an hypothetical line. When I say hypothetical line, just a line. Now we are looking at only the surface of this A, B, C, and D, just for understanding of what I'm trying to explain. Now at the surface here, there will be intermolecular forces that act between molecules. We act in different directions. You can see some we have, you have outward force, and some we have what? You can see some forces are coming towards here. So what we try to say is that there will be what? Between this hypothetical line, the forces that act in between it are always acting in the direction normal. You can see normal or perpendicular. But if we consider the edge of this cube now, as this is a hypothetical line, the force will only act in this direction. You can see this is the direction of force we are considering. Now, what you see here is that as we are looking at this, the force that acts between the layer, these are force, I'll call it force on the surface. This is also the force acting in different direction here, which balance out each other at the middle here. While the extreme end, the force are acting only in one direction. So because of these forces acting on the surface of the liquid, it will now make the liquid to look something like this. Just for you to see, I will have drawn another one, but because of time and because of where we are still going, we just need to speed up or accelerate our pace. Now, doing that, we can say because of the force acting on this particular line. So I want to define, maybe in an advanced way, I can say the force or intermolecular force that acts between the surface of a liquid when an hypothetical line is drawn on the surface, the force that acts normal in that direction. So the force will now stretch this liquid, the surface of the liquid, and make it be something like this. Now, you will now see something like this on the surface because all the forces are meeting up at one point, and what the liquid layer here will be stretched. You can see what I'm trying to say. They are now stretched, just like when you talk about what? Wire. When you try to elongate wire, wire will onward stretch. The same thing happens on the surface of the liquid. And that is why in this particular place, the force acting on this particular place with respect to that particular line, we call the surface tension. So we can write in continuation to this and say what? We can also write another important point that surface tension is expressed mathematically. Surface tension is given numerically as we write surface tension in physics as T. Please keep that in mind. It's given as the force. We say force acting normal, or you say acting perpendicularly per length, unit length. So we can give the SI unit in what? Force are measured in Newton, and length is measured in meter. So we say the SI unit of this is measured in Newton per meter. I hope you understand this. And this is the interpretation we give to surface tension in physics. So we must always keep this in mind that the force that acts between an hypothetical line or any line, which is always normal to it, such particular force is called surface tension, and it is given by force per unit length in terms of what that's. Now, another thing I can also bring to us to understand very well, for us to understand the concept very, very well, is to know that normally we know liquid are flowing, as we can see, illustration given, at below the surface here. There is what we call sphere of influence. Well, for A-level students, it may not be needed. But what I'm trying to say is that for when we talk about force, sorry about that, just a small one for us to understand now. You can see on the ear now, there is what we say water will start flowing at different directions in terms of molecular force, jingling around and moving from one side to another. When they move together, the forces now, we now talk about the flow. It's because of this sphere of influence. Now, this particular sphere is now responsible for the force that is also acting on top of the surface, but narrowly. Don't let us go into what is not needed for now. For your level and for the application of JUPEM and the other exam, as you call it, level here in our country, you should always keep it at the back of your mind that it's just a same force that acts by hypothetical line, which is the length. That particular force we call surface tension. And the numerical, if you're asked to calculate, all you need to do is to understand what is cut between different layers. And be careful because you have different positions. Surface tension the force acting at a particular body might be more than one at a particular point, and it might generate different surface tension. So we need to understand that when we are considering different shape, we look carefully into the position, so to know the amount of force that is acting with respect to an hypothetical line. So this is the way we relate this in physics, and we have to keep it in mind. And that is the introduction I'll give into this topic as part. Its significance is expressed numerically, and again, it always acts on the surface. Now, a very good example to before we move to the next slide, which you can also give of surface tension, is we have quite a lot of examples that you guys might actually try in terms of experiment. A very common one is a mosquito larva, cockroach. A cockroach moves on what? When cockroach is placed on water, they stay on top of water. So we can give lots of examples. So we can talk about, and the reason is because, so we can say, let's put that in note. We can say some examples of a real life application of surface tension are Can write as many as you want to write, but just limit it because I've given more explanation and talk about mosquito larvae, larvae, the way it's done in biology, moving on top of water. Another one is cockroach. These are insect stuff because I have seen a lot of question on top of water. And also talk about other things, umbrella. Look at the umbrella, for example. When the inside of umbrella is touched, you can see when water droplets, you use an umbrella to trace. What I'm trying to say, in order not to cram, you need to understand constantly. It's just that the force that makes something to act like a stretched, when something is stretched like an elastic material. So that force is what keeps them on top of water. So anything that you can think of, and it's only acting on the surface. It is not acting throughout the whole bulk of the liquid. So this we call what? Surface tension. Be careful about that. And it is only on the surface. Don't make mistake. There are a lot of illustrations. It's not only a sick umbrella, which I said, you can give a lot of illustration. It's just for you to know that whenever you are thinking about surface force, what comes to your mind is, surface tension. So, and this is just what I want you guys to know about the introduction. You can also define in terms of the formula. Physics accept formula definition as a force acting perpendicularly per unit length or per hypothetical line, which is the unit length. So this is how I want to stop here. I'll move to the next slide to explain the next part of it, and we move in what? In sequence. About the next one, we have some important facts about surface tension. Now, about important facts about surface tension, now that we are able to explain the concept of surface tension, we need to put down some facts so that we can actually when we are faced with some other things in some questions that are multiple choice questions, we will be able to understand it clearly. And it will be like a direct information from what I've given to you. So writing some important facts, as we have studied that it is only the force that acts only on the surface of a material we call surface tension. And because of that, it depends. Let's put down a note. I think it's always good to put down a note. Wow, it depends. I believe the back can say it depends on the nature of the liquid. So as I've explained in the previous slide that surface tension does not depend on anything except just the nature of the liquid, or basically you say intermolecular forces. So that is another way to understand that. Another important fact I think we can put down here to understand the concept very well is when we talk about another one, which I think is also good for us to know about the unit. Surface tension is given as surface tension. Sorry about that, I'm having issues here. Now we have a surface tension is a scalar quantity. Surface tension is a scalar quantity. So students should be very, very careful about that because it is only the force that acts within an hypothetical line. So we are not talking about the particular force having any impact on any other thing. We need to keep that in mind that the force between surface tension is the force that is acting between a particular line. So it does not depend on any other factor than intermolecular forces between it. So always keep that at the back of your mind. It is not vector because you have force. It is a scalar quantity as it does not depend on any other parameters except the intermolecular factors. So another thing we can also keep down on this note to have a good one is that we can say impurities. Impurities lowers you can say lowers or decrease. Please be careful about that. Lowers the surface tension of a liquid. So that is another important fact I believe we need to keep down. I'll keep at the back of our mind. Impurities lowers the surface tension of a fluid. Now, about impurity, we can also talk extensively on this to understand impurity can be in two forms. You understand what I mean by that? There are some impurities that are soluble, and there are some impurities that are what? Insoluble. From your knowledge of chemistry, you can always have it at the back of your mind that when we talk about soluble impurities, what happens? You might say the soluble impurity might increase or decrease surface tension. So technicality might come in, whereby insoluble impurity will always decrease. So why are we saying this will always decrease? And this may increase or decrease. So it depends. Now, the question is that we have explained so far so good that surface tension acts only on the surface. And because it acts only on the surface, if you put something that is not going down, what do you expect? It will lower the intermolecular forces that is active. So that is why you need to understand the concept very well. But if it is going down, it is two things. It might reduce it, and it might not reduce it. So always keep it at the back of your mind, because when you have questions that ask about soluble and insoluble impurities, this is the way we analyze that, and that is that about that. Another thing I think I need to talk about so that we can move or increase our pace is that the effect of temperature on surface tension. We can say temperature. I hope you know what we call temperature, the measure of average kinetic energy. So if you are talking about intermolecular forces, we are measuring it with what? Average kinetic energy. So intermolecular force is responsible for surface tension. So if we talk about temperature, please, we are always considering we always neglect other factors because there are other conditions, because there's another thing called critical temperature, because temperature will tend to increase toward the surface tension to a critical value before it starts decreasing. Hope you understand what I'm trying to say. What I'm saying in essence is that the effect of temperature on surface tension is what? Temperature, we can say temperature increases. Let's put that down. The surface tension, I'm writing as ST, of a liquid to a critical point. So what I'm trying to say now, my dear student, is that the effect of temperature on the liquid is that it will increase it to a particular point, which we call the critical temperature. So at a particular temperature, which we call the critical temperature, you start seeing what's the surface tension going down. So these are little things you can keep in mind. And for you to understand this very well, you know impurities will lower. Please keep that at the back of your mind. Whereas temperature will increase. So let's move to the next slide to quickly talk about the next thing we need to know about the topic of surface tension. I believe we are moving forward in this checklist and slides. We are going to be getting the surface tension very well. So we move to the next one. Wow. Concept of surface energy. Now, about this, my dear students, we need to understand what is called surface energy. And to understand this very well, I will take us back to the topic of elasticity and work done. Now, as we have discussed, maybe we'll put down a note. As we have discussed that the surface, we can write the surface of a liquid acts like a stretched string, acts like a stretched string, and ends it will store some elastic potential energy. So to understand this very well, what I'm trying to say is that from a knowledge of our elasticity and elastic string, we know that when the wire is stretched, work is done. And the work that is done to stretch the wire from one particular point to the other one is taken as the product of force and the what and the change in displacement in the direction. So now here also, because we said the surface of the liquid acts like a stretch membrane. That means at the surface of a free-flowing liquid, please, you have to listen, the particular energy that acts on the surface of a free-flowing liquid is what we call what is surface what energy. Because there is an energy for it. We know there will be a force acting hypothetically on top of the hypothetical line. This particular force will now be moved by a distance. So if it was moved by a distance, we know what? When you stretch a wire, work is being done. And when work is done, it is always what? In form of what? Elastic what? Potential energy. So energy is stored when work is done under the concept of work, energy, and power. When the work is done, energy must be stored. Because if there's no energy that is stored, when you stretch that wire, it will not be able to come back to its what? Original position. But because it has stored some elastic potential energy, which we call potential energy. But in liquid, here, the potential energy that is stored when it has been stretched or further stretched is not what we call what? The surface what? Surface energy. So we need to understand this very well. And to understand this, we need to do some diagram and also explain some concepts. Now let's look at a shape. I think I will go for a YouTube shape, something like a YouTube shape, which I think will do the work for me the way I want it to work. For understanding's sake, let's consider a YouTube shape to some value. So we have, let's just consider this small shape for the sake of understanding. Then we have, let's consider this and use this for, sorry guys, diagram not drawn to scale. It's just for us to understand what I'm trying to say. So let's say we have this type of shape. We have something like a tube that is slanted. I just want to slant it so that it will go with what I want to explain. Let's say now on top of this YouTube source, so we have a slider. I hope you know what we call a slider. That is what can slide. A slider is placed. This is the slider that is placed on top of this. That's for illustration. This is a slider. And inside a part of this, we have a soap film. Just tell you we have soap film, you know, soap film, soap, S-O-P. So we have S-O-A-P, not S-O-P. S-O-P in physics is called system of particles. Now you have this, a soap film. Now this is a soap film for understanding's sake. And as we have already studied, now soap films are both placed on top and under, as you can see, for understanding's sake. Now, from what we have studied so far, we know that on the surface of this soap film, of this hypothetical line, this line now, surface tension we act. And the surface tension will only act in this direction. And you know the reason we are taking the length of the slider to be equals to what? To be equals to L. I'm considering the length of the slider to be X and place. Now, on top of this soap film now, we have a force acting at this point. We know that, and surface tension we what? We emanate, we generate, we start. So let's say we take the force acting on this as F, and the same thing under the what? Under the on the top of the soap film, another one we had under the soap film. Now what we are trying to say here is that when we consider this, we can say the surface tension, as we have said, I will be representing surface tension with T. I'm only trying to show this so that we can all follow what I want to bring out. The surface tension is given as a force acting per unit length. Now, if we consider the force to be F, we said there are two words. Now we can make the force acting here to be equals to what? We have a LT. As I am taking surface tension to be T, I have only cross multiplied. But if you look at the soap film, there are two conditions. One is acting on top, another one is acting below. I'm pointing that, I hope students can see what I'm trying to say. We have two surfaces, up and down. So we can say the force acting on this thing, we can say the external force or force. The force acting on this diagram or illustration, the force acting on the soap film is equals to what? 2LT. I hope students understand where the 2 is coming from. The 2 is actually coming from the force that we've talked about, up and down force. Now, similarly, let us also assume we are moving, or we are now what would apply another force to move this slider to another distance. Like now, I am moving this to another distance of what, let's say the distance between the first one, is a slider. Now it is moving to a distance of, let's say the distance of what? It has changed to a distance of ds by application of what we call external force. As in, if you want to move something, no work is done when distance is not covered. We might have learned that in our class 9 or junior classes. Now, what I'm saying now is that I'm applying an external force, which I will call F external now. F external to pull. Yeah, you are pulling it to yourself to a distance of delta x. So we can say that what, for equilibrium to set in, the external force now we balance what will be the same thing as the force acting on the what, on the soap film. Now directly now I can say fine, because I have applied a force and I have moved this by a distance, what happened? Work has been done. So from the concept of work, energy, and power, we can say the work done directly here, the work done in moving this is the same thing as what? The product of the force, that is F external, multiplied by the distance. I'm only considering the distance of what? Delta S. Or basically, maybe you write whatever. Delta S means change in distance. I hope you understand that. And I'm taking that as delta S. Now, directly now, we already know that the force acting on the surfing will balance out the force external. That's what I mean, like the external force is given here as look at this. The force acting on top of the top film is twice of what? LT. So you can say 2LT delta x. I hope students are following this because we are going somewhere. I hope you're understanding what I'm trying to say. I use a force to drag the slider and move it to a distance of x. I haven't done that. What happened was that what work was done. And when work is done, the work that is done here, what will happen, like I said, when work is done to move an object, what will happen? There will be somewhat elastic potential energy. So because work is done, we can note that what? Energy, let's just focus, energy will be stored. What is the name of that type of energy? We call it what? Potential energy. Please keep that in mind. So now, the next thing we want to do now is that now, okay, fine, we know that the work done on the body is now equals to 2LT change in what? Delta X. We can also consider the area because the area here is changing and we need to understand something. Now, area, from what you have learned before, the area, let's consider that because we are changing the what? The dimension. You can see the area here is changing. So let's say the area of the slider, generally area should be, you can see, area should be L times what? Length times what you can say. This is the slider. I hope you understand what I'm trying to say. Length times breadth. Length times breadth. My length is L, because I'm considering the length of the slide of this thing to be equals to L. Then my breadth is what? Delta X. So I can say the area covered by this is L delta X. But we need to understand that on top of the soap film, we are considering the top and the bottom. So I can say total area. I can put that down. Total area can be equals to, if one area is L delta S, then total area will give us what? 2L delta X. So substituting that in the work done here, we can now say the work done concept is always easy if you follow through. Work done is now equals to, guys, watch this. What we have here, what's that? We have 2LT delta X, where T is the surface tension. So yeah, and the area is what? 2L delta X. So we can say 2L delta X is equals to area. What we have here is what? Tension surface tension multiplied by what? By the area. Like I said, work done is stored in form of what? Potential energy. That is, the work done is what? Is potential energy. So numerically in physics, potential energy is denoted by U and is equals to the what? The tension multiplied by surface tension multiplied by the area. So we can make the surface tension subject of formula and say it is equals to what? The potential energy divided by the area. This is where we are going, and this formula, like as usual, you have to keep in mind and make sure you always what? Have it at the back of your mind whenever you are giving an expression in numerical that has surface energy and has surface tension and as well as area. Surface tension is defined as the ratio of surface energy per unit area. So always keep that in the back of your mind. And this is another definition you can give to surface tension. I hope we understand this, and I hope we are going to keep this formula in mind, because when we have illustrations and numerical that is going to deal with all these, we should always remember all this. So that, guys, that is all about concept of surface energy for now. What I'll do now is I'm going to move to the next slide as usual, and let's see what we have in the next slide to talk you through it, guys. Wow. Now, the next one is an angle of contact. Angle of contact is another important topic under the surface tension. And to understand angle of contact very well, we need to introduce ourselves to what we might have studied. And I hope we have studied this in our junior classes or in our early classes. Now, about angle of contact, before we write anything about angle of contact, let us first study what we call the adhesion and cohesion. I think we need to talk about that first. Adhesion and cohesion. Now, in early classes, we might have studied that the force of adhesion, maybe we should write, I think it's good to define, is the force that acts between the force of attraction between the adhesion is defined as the force, just to cut it short, the force of attraction, between unlike substances or between molecules of different material. Whereby the opposite is cohesive force, you can say cohesion is the force, or you say intermolecular force if you want to write. There's a force of attraction between like substances. So this is the definition we give to adhesion and cohesion in junior classes. And you can always keep it at the back of your mind, because sometimes you might be asked to define this directly in your theoretical question. Now, having said that, the next we all need to understand is what we call angle of contact. To understand that very well, I will take us through by drawing a simple diagram. We have something like this as usual, or we can just say layer of a liquid, anyhow you want to take it, in which it is filled. What I'm trying to do is my usual way. So looking at this, guys, we can say, let's say we have a liquid inside a beaker that is filled to a certain point. Now, because the liquid is actually having some point of contact with the beaker or with the material or container in which it is filled. You can just double up the container for you to see well. Don't mind my diagram is not going to scale. Now, if you see this, there's a contact here. Now, what we say is that because we are talking about adhesive force and cohesive force that act between substances. We said the one that acts between substances of the same, I'm filling this thing with water just for better understanding to that level. So now what I'm trying to say here is that at this point now, from what we have just studied, we said the force that we act, there will be a force that acts between this surface, the surface of the what, of the solid here, of the beaker, and that of the water. And because of that, there will be a force that will pull this, let's change to, now that will pull this in inward direction. In inward direction, as you can see, you see the force we act between the surface, and that is what the cohesive force. Cohesive force. Another force will now act between this container and it will act outside, as you can see. So this one that pull it away from the liquid is called what? Adhesive, what you can see, adhesive force. So students should understand something here and not scrap. Now, the cohesive force is also, we are saying force that act between molecules of like substance. You can see this is still the water surface now. As this is the top of the water, there will be another one that we had in this point. So this particular force here is also what? A cohesive force. Now, in generalization, or to understand the concept very well, we can just say we have, so we have this, just for understanding's sake, very quickly. So let's just take that to bring it out very well. What we are trying to say is that when we try to join the adhesive force and the cohesive force between layer of liquid, what we do now is that all the adhesive forces that are acting against what the layer of the liquid that is going outside, as you can see from the diagram, we all act in a particular direction, and they always act in this direction. That is what I want to show you now, which you just need to focus on. Now, the force we are talking about, this is the liquid layer, diagram not drawn to scale. Then the adhesive force we are talking about, all the adhesive force we tend to act in this direction. So it's just like saying the direction of adhesive force, every one of them will act in this form, adhesive force. All the forces that are acting away, we now act along one line, which is in that direction. Then the cohesive force we are talking about is acting in more than one line, because we have a cohesive force that is also acting in the same line, but the direction is inside the liquid. Now, this cohesive force is called the horizontal cohesive force. So I'll call that one horizontal cohesive force. I'll call that maybe FCH. I just want to call it a name. It doesn't matter. And there will be another cohesive force which you need to keep in mind. There's another cohesive force that is coming in. There will be another one that will be acting in this direction, which we call the vertical cohesive force. You can see cohesive force is always acting inward along the line. So this is the vertical cohesive force. So what I'm trying to say now is that the direction is another cohesive force which is between the line. So what we call angle of contact is the angle that acts between the contact of liquid and solid, or liquid and the material, or angle between, I think it's better, between the tangent line that is drawn from the what? Adhesive force and the cohesive force. But the issue we have here, for understanding's sake, is just that there are two forces. There are two forces that is acting on this particular portion. That is, I'm talking about the horizontal line. Where are the forces? We have the cohesive force that is acting horizontal, and the adhesive force that is acting also in the direction of horizontal, though they are not acting in the same line. They are acting in what? In different lines. We need to understand this, that what we decide, the particular force that is acting at this side is the what? It depends on the magnitude. Let me put it in that way for us to understand. For example, there are two forces that is acting on what? On the vertical, on the horizontal. To know which one is taking control, which one will take over, it depends on the shape in which the liquid is moving. What am I trying to say? Don't let us take too much of what all this thing. Don't let us make it hard for ourselves. What I'm trying to say is that there is an adhesive force, there is a cohesive force. The adhesive force is the force that acts force of attraction that act between what substances that are not of the same material, unlike substances. In liquid, both adhesive and cohesive are going to act on it. But there's one thing about the cohesive force. Cohesive force we are talking about can act in two different ways, horizontal and vertical. So adhesive force only lies on the horizontal. We also say we have horizontal cohesive force. So what we are trying to say now is that for us to know the shape at which the liquid, liquid is filled up here, we need to understand that, and we need to keep that at the back of our mind every time. Now, so far there is liquid inside this container. Liquid will start flowing, but the flow of liquid will now take a particular shape, which we call meniscus or anything you want to call it. So the shape it will take depends on which of the force is what is having the more power. For example, what I'm trying to say now is that if the horizontal adhesive force, if the horizontal cohesive force is greater than that of the adhesive force, then the shape of that particular thing will look somehow. Of the liquid will be somehow. The meniscus will be somehow. If the horizontal or the adhesive force is greater than that of the cohesive force, you always keep it at the back of your mind. That's what the shape will always will look somehow. So to understand how the shape will look like, let me quickly explain that in this. Now, for the first case, we might just take this that if the cohesive force, now horizontal cohesive force is greater than the adhesive force. You can see where's the direction of cohesive force of the cohesive force is what inside. What you notice here is that this is something you are going to have. Diagram not done to scale. I just want to bring out something for us to understand. So now, if I'm taking the first situation, if the cohesive force, horizontal cohesive force, is greater than the force of adhesive force. So the liquid layer will be something like this, as you can see. It will form something like that because it is going inward. Because we are talking about the cohesive force horizontal is greater than the adhesive force the adhesive force. But if it is the other way, that is the way in which the liquid will flow. But if it is the other way, what you are going to see is something like this. You just need to understand this very well. I'm going to see something like this. Now, if it is the other way, that is the adhesive force on the horizontal is greater than the cohesive force that is on the horizontal, you are not going to see something like this. The liquid will now flow something like this. It will flow like this, fine. As you can see, I need to bend it a little bit. Like I said, diagram not going to scale. So for this type of flow, you expect here you are talking about adhesive force is greater than horizontal cohesive cohesive horizontal. So this talking about different meniscus, different shape that a liquid will take. What we need to keep at the back of our mind is that it depends on which of the adhesive force or which of the cohesive force is if the cohesive horizontal is riding the adhesive force, you have this type of meniscus. And don't forget that what we have before, if you can remember, is that we have a particular force, the other force that is acting in this direction. We have another one in this direction. Please watch. This is the point of contact. There is a force that is acting between the layer of the liquid here before, which we call the normal cohesive force. Then we have the horizontal cohesive, the vertical cohesive force is also acting downward. Then when we try to draw a tangent line, which I will try and draw now, I want to draw a tangent line for understanding's sake. Let's draw a tangent line on top of this meniscus. If we draw a tangent line on top, diagram not drawn to scale as usual. So what we are talking about now is that I've drawn a tangent on top of the meniscus, the shape here. So the tangent, you can see point of contact now. We're talking about point of contact, but maybe I should either use a good diagram as well to draw out my horizontal, the force here that is acting for us to see the angle very well. I think that would be better. Instead of using that line, let's use this particular line. So you can neglect this first line as this that is coming in here. This is what I'm trying to bring. I've drawn a tangent line. We are now saying the angle between the tangent line, and the vertical, you can say, and the vertical cohesive force, the angle that it make is now called angle of contact. You can see here, this is it. For us, this is the second one that is coming down. This is the one, and this is the angle that is between here and here. As you can see, this theta here that you see here, my dear student, is called the angle of contact. And in this case, you don't need to be told that this angle here is greater than what? Is greater than 90 degrees. So in this case, theta is greater than 90 degrees. And when theta is greater than 90 degrees and not up to 180, in your mathematics, you call it an obtuse what? Obtuse angle. So my point of analyzing this stuff is because of some other kind of competitive exam that may require a kind of definition that is up to the task. As in, I'm talking about a standard definition. So what we can conclude from what I've given out here is that when the obtuse angle form, between the point of contact of the adhesive force and the cohesive force is what is called what? Angle of contact. A layman or a beginner can define angle of contact, which is also acceptable, as the angle of contact. You can write angle of contact, for a simple definition, is the angle between, this is just a layman definition, the adhesive force and the cohesive force. So we need to understand this also because it's very, very important. So angle that makes between the adhesive force and cohesive force, that is just for beginner. But the angle can be in two situations. I told you it depends on which of the horizontal force is taking over. If it is the cohesive force, as you can see in this situation, the shape of this thing will slide inward. The shape of the liquid will go inward because the direction of this is inward. But if it is this one that is taking over, look at the way. It's like this thing is going upward. You know, I didn't actually draw a well, but it should be like this, as you can see. So that is what I'm trying to show. So now let's quickly understand this as well. Remember, there is also another angle, which we call the inward from the point of contact, you know, that is acting just for us to show. That is inward cohesive force, which we have discussed about. The cohesive force that is here. It's also cohesive force, F cohesive, like what I've shown you, F cohesive. This is it, F cohesive. So cohesive forces are acting in different directions. And there's another one that will balance it. So we draw a tangent as usual. We draw a tangent line. You know what we call a tangent line between this. You can see. If I draw my tangent line, that tangent line will come something like this. That's for us to see. Diagram not drawn to scale. I will need to extend this, before, so that it will balance what I want to see. Let me do this. Just for understanding's sake, please. What I'm doing is for understanding. Let me draw my tangent first. Let the tangent line come. Tangent is a line. You know, everybody should know tangent. Diagram not drawn to scale. That's the tangent line. I'm drawing the tangent on top of the steepest side, just like what I've drawn here. That's the tangent line. It can be extended if we want. Then remember, there is another force, which is what I want to show the other time. This particular force here, I need to show that that one must be bigger than that one. And don't forget that we are talking about another particular force, which I will show first for understanding's sake. We are talking about this particular force. This thing should have been narrower, but because of this, then we have the angle that is being made from here to here. You can just see that it's made between this and between the tangent and that of the what, and the one that is coming here. Just like between the tangent and the one that is coming here. But this time around, if you watch very well, you are going to see that this angle is what is less than 90 degrees. As you can see, the right angle triangle. The angle here is less than 90 degrees. And you call angle less than angle, you get what? Acute what? Acute angle. So what am I trying to say, guys? If the angle of contact is an acute angle, we can also infer some other thing, which I believe we might have studied in early classes. But if we are yet to understand the concept very well, what I would advise us to what to do now is to what to write the short notes down. Now you can say now, if angle of contact is greater than 90, what happened here? What happened here is that what this particular force, what do you call this one? The cohesive force is greater than the adhesive force. But in this case, what happened? The adhesive force is greater than the cohesive force. Now, we can give an illustration to this, and this is what I believe we might have studied, I hope. And I said, if not, you put this down. We can talk about the concept of liquid wetting gas, concept of liquid wet or do not wet glass. Now, what am I trying to say? In this case, for you to understand very well, which is what I want you to keep at the back of your mind, and it's also very, very important for your examination. Now, you can always keep it at the back of your mind from here. That's for this particular case, if you consider this very well, or we look at it very closely, in this case, with an obtuse angle, and we say here, what happened is that look at the direction. Guys, what happened? Look at the direction of the meniscus from here. The direction is going outside. And when it is going outside, what happened? We say liquid here. Liquid do not, right? Liquid do not wet glass. Liquid do not wet glass. And the reason is what we call, the reason for that is because what? What's the answer, guys? The what? The cohesive force, right, is greater than what? Than the adhesive force. So it's just not about cramming, but about what? About understanding. So in the second case, look at the meniscus here. Look at it. The meniscus here is going inward. It's going inward. So because it's going inward, what we are going to say here is that what? The liquid we what? We wet glass. I mean, when something is going in the direction of the motion of the liquid, what happens, guys? It will wet it. Now we say liquid or liquids wet glass. So far, we have our liquids, fine, I'm back. Liquids wet glass. And the answer to this is because what's the answer, guys? What happened here? Adhesive force or force of adhesion. Anyhow you want to write, you can write it that the force of adhesion is greater than the force of what? Cohesion. Adhesive force is greater than cohesive force. So you don't need to stop yourself too much on all these things. All what you just keep in mind is that, and the commonest example we see in our test material is also examples is water and mercury. I believe you still remember in junior classes. Or for the sake of writing, you can say water wet glass. Like this example is water. Mercury rather. Mercury is written as Hg for those who don't know. You can just write that. And for this one, you say water wet glass. Yeah, I've seen a lot of questions during my teaching experience when I'm still teaching in classroom that water wet glass and mercury do not wet glass. And the reason is because we've just explained that because adhesive force is greater in water than the cohesive force. And I said something, if you are following me very well, I said it is because of the shape they are taking. You know, one is going like this, don't mind my hand, and the other one is going in the direction. So there are two shapes, two meniscus. So the meniscus we are talking about are of two. We have what we call convex meniscus. And we have what we call the other one here, we have what concave, as in the shape they are taking, concave. So when we say something is concave, you understand? And when we say it is what, because when you talk about meniscus, we are talking about the shape it is taking when what you are measuring the angle of contact. So concave meniscus and convex what meniscus is what I've been talking about the shape they are taking. So if somebody say, we're making water well gas, concave meniscus. Mercury do not wet glass, convex meniscus. You are correct. But you want to explain or you want to take them through, you can quickly say concave meniscus, adhesive force is greater than progressive force, progressive force is greater than adhesive force, anyhow you want to do it. So please keep this at the back of your mind. It is very, very important for you to understand this concept, the angle between adhesion and cohesion is called angle of contact. And when we talk about liquid, you want to quickly talk about the last one, which I believe you need to understand. If you say something wet glass, in this case, if it is wetting glass, this is what you are going to see. The angle of contact will be, let's say we have a ground and we have an object that is like this. Then you are dropping something on top. The angle this thing makes here is the angle of contact. But if it is the other one here, if you consider the same thing, what you are going to see is that it will the direction of the angle will be flattening, almost flattening. Let's say the object was dropped. So the angle this thing make, it will be the obtuse angle that it makes like this. So what we are trying to say is just what I've explained. So because sometimes you might see diagram and you'll be looking at, what's this one? What does this mean? My point is convex meniscus, concave meniscus is talking about adhesion and cohesion. When we say meniscus, we are talking about the shape or the turn in which it takes. And the turn is determined by the adhesive force and cohesive force. All these are just intermolecular forces that are acting. So it's just to understand how these intermolecular forces are acting on what? On a liquid. And that is why we have taken surface tension, we have taken cohesive and adhesive force, we have taken angle of contact, and the meniscus they form. And I think the last one about this should be in the next slide. I believe, because I do tell you I'm not the one that prepared this slide, it's always prepared by my students. Now, the last one should be capillary action. So let's move to the next slide and let's see what we have. Oh, wow. Now, about this, we have a capillary action, or what you call capillarity. Now, I will not take too much of our time on this because I'm still going to talk more about this capillary action under the topic of kinetic theory of gas and do a lot of numericals as what we need. Now, to understand capillarity or capillary action as the case may be, we might first take down a note, which I believe is important. Now, to understand this, my dear student, we can say the rise and fall of a liquid in a narrow tube. I'll give you the simplest of definition. Due to intermolecular forces, is called capillarity, or you say capillary action. Capillarity. As we have studied, so far so good. We said when we place a narrow tube, as you can see from here, let's just look at the illustration. I'm still coming to water and mercury. We've talked about water and mercury and why it's wet glass and why it doesn't wet glass. Water with wet glass, concave meniscus. Mercury will not wet glass, convex meniscus. We've talked about that. You can see the meniscus are different. Look at concave meniscus. Look at the way it's going. Look at convex meniscus. Look at the way it's coming. So you have to understand this. It's just like that in reality. All this can be what can be done. Now, we can also say because we are only considering the surface of the liquid, we can always explain all this. Now, I'm going to use this diagram to quickly take one of these because of time, and I still have the illustration to talk about. And the normal hour I've been given is always 1 hour, 5 minutes. So I'm not quite sure if I have used up to that. But all things being equal, I need to increase my pace. So and don't worry, guys, I believe you get it. And you can always download the video and watch over again, and you take a note. You cannot be watching the video without taking the notes. It's not going to income. So moving on to what I'm talking about here, my dear student, is that the force or the rise and fall. We know that if we put a narrow tube inside a fluid, what happens? The fluid will come we come what? We flow through it. Let me use that simple English. And again, the narrower the tube, the what? The more what? The increase in the what? In the level of the fluid. You need to understand that. And this is exactly what happened here, my dear student. You can see the narrower the tube, the what? The increase in the level of capillarity. So we can say the you can say capillarity depends on what? On what? On the radius of curvature. Do you understand what I mean by radius? I had the radius or the distance of what between the tubes. So in narrow tube, we have high capillary than what? Than a, a wide tube. Now, to understand this very well, because we need to understand this with respect to the height of what? Of capillary tube above water. I'm going to take this one only to explain the concept very well. Now, as we can see here, guys, this is a concave meniscus, and you know why it is concave meniscus. I don't need to tell you adhesive force is greater than what? Cohesive force. We've done that in the previous slide. And let's take 2 points in between the layers of this. I'm going to take the point right above this capillary action. I'll take the point as point A. I'll take the second point right below this point. I'll take it as point B. From what we have studied, let's quickly derive or bring about formula. I just hope you can follow me through. Now we say the pressure at A. Now we can say pressure at A from what we have studied is directly equals to what? The atmospheric pressure, which we call what? P atmospheric. I hope you understand that, my dear student. Hope you still remember atmospheric pressure, because it is not this particular point, liquid is not reaching there. Or is there any layer of liquid here at point A? No, it's only the atmospheric pressure. Please, you have to smile. The next one is, let's consider the second point, which is directly below the surface of A. So we can say the pressure at B now will be some kind of less pressure or lower pressure. Remember what happened to pressure? Pressure increases with what? With height. Now B is right below what? Right below A. So we can say pressure at B will be what we call our normal pressure minus what? You can say the pressure will be H rho G. Everybody knows the formula for pressure. Then we say minus. Why am I minusing? Because it's below. Now, I will say it's below. We have a minus 2T by R. My dear students, hope you still remember what I call 2T by R. Why am I subtracting from 2T by R? What is T? Surface tension. What is the formula for surface tension? Surface tension is force per unit what? Length. Now, I'm taking what? The surface tension at two hypothetical lines. Abi, you can see the force. The force acting on each of the line is what? LT. You remember that, but we are taking with respect to the radius of curvature of this one. So at each of them, we have what? Surface tension here, another surface tension here, divided by the radius of curvature. So because we are subtracting it, it is going down by a distance, and the distance we are going to consider here is what? Minus 2T by R. Now, let's take another point inside this layer. Let me use another color. For understanding sake, this is the last aspect, my dear students, is because we need to understand all these things. And I told you, physics is quite simple if the knowledge is what is taken well when you are reading. You don't need to read like other subject that you have to read over and over again. So once you know physics very well, you are going to get it. Now, about this, I'm taking another point, which is exactly here. I call point C, exactly on the same horizontal line as this. I'll call point C. Now, let's consider the pressure at point C. I can say pressure at point C, my dear students, is the same thing as, now, we don't need to waste our time because we have already talked about this. We know that the pressure at point C is also going to, because it is at the same horizontal line. And because it's at the same horizontal line and it's facing this, we say it must be, the pressure must be equal to this, which is the same thing as what you say, P atmospheric. So now, if I want to take that now, as the liquid starts flowing, you know, as you put this thing inside it, what you see is that the direction of this one will what? The liquid will start rising, right? As the narrow tube, as the tube is dropped inside it, because of the concave meniscus. We have talked about that. Because adhesive force is greater than cohesive force. And that is why the meniscus you are seeing here is what? Concave. I hope you are following. So now what you need to keep at the back of your mind is, because of this, there will be an increase in the height. So what you are going to see is this situation. My dear student, are you following? So now in this situation, now when this thing starts rising, then the something rise above or to this particular level. And that is what we are trying to say. I will only do one part, the other part you can derive on your own. So now what happened? A will now be somewhere around here. I want my student to communicate. A is here, right? We have A is somewhere around here. The B we are talking about will be directly above here, right? B here. And the C will remain at this point. It is only the level of A and B that has what? That has risen. Or that is raised, anyhow. Now, directly we can now say the new pressure. Now we can now say, okay, the pressure at C now, which we say is the atmosphere. We can now say here, the pressure at C now, or we say another pressure, which is the third pressure at C, will now be the atmospheric pressure. You can say pressure at C will be atmospheric pressure plus what? H rho G, which you have already considered. Or we can say the atmospheric pressure plus pressure at B. Let me just put it like that for as in the pressure at this point C, which is constant here. We now take the pressure at what? We are talking about H rho G plus the pressure that is coming from B. So plus pressure at B. So directly I can just substitute my parameter and say pressure at C, which is the same thing as atmospheric pressure at the beginning, is now equals to atmospheric pressure plus what is pressure at B? I'm substituting the parameter you have here. Please, you have to communicate H rho G minus 2T over R. I love this. Wonderful. What happened? P atmospheric gets cancelled out as usual. What happened? We can substitute this as directly. Let's change to a black. So we say here, you can say this will cancel. I hope you know the mathematics as well. This comes to the left hand side, it will be negative H rho G. This comes to this, it will be what? Negative 2T by R. So what I'm trying to say here is that if I move this, negative will cancel negative, which you can do it on your own. H rho G, and it's a black, H rho G is now equals to 2T by R. Please, what does R stands for? The what? The radius of this meniscus. So directly we can make H over a formula. I hope my students are getting this. H will be equals to, directly, we can say H equals to, and for those of us that are not that good in understanding all this stuff, what we just need to do is just do it one by one. So let me take my time to explain to you. What do? You cross multiply. This will be H rho G R is equals to 2T. What do you want to measure from that? The height at which it has risen. You know, it was at this level before. Now it's not at this level. Now, what happened now is now H will now be equals to 2T divided by, what do we have left? We have a rho GR, or G rho R. Anyhow you want to write it, just write it in a way that you understand. Rho GR or G rho R. So this is particular formula we use for calculating the height of a capillary, the height of a capillary tube, which is quite important for some numericals under your what the A-level exam. Then it doesn't stop there, because sometimes you might be given angle of contact. To classify angle of contact with respect to, please keep this from my mind. I just want to finish it up here now so that we just call it a day. I'm being signaled to stop this class. Now here we can directly look into in continuation by bringing a sphere on top of this liquid surface, just so that we can consider the angle of contact. I want to bring in a sphere, and doing so, I'm going to have something like this. I don't even know how a sphere look like nowadays. All I know is that I will bring a sphere. Maybe I'll bring this one is no sphere. This one is up. So I'm going to bring a sphere. I think I've done that. I believe you can see, my dear students, into that. Should I paint it? No, I'm not painting. So now you have a sphere right in point of that is having, we have talked about the radius of the curvature of this one is nothing but what? Capital letter R. Now we are taking this sphere just for understanding sake. We've talked about the direction of the meniscus. So which is at let's just take a close study. Don't worry about this. It's just about direct substitution of formula, but I just want to show you because I love showing or to prove most of what you can prove. The only thing I may not be able to prove to you is the formula that is derived from experiment. Only if we go to the physics lab and I try to do the experiment to show you guys, which I have some video in which I've performed in the lab. Later on, you'll be seeing some of them on the channel. Now you have here, This is we have the radius of this, the radius of this circle. Everybody know the radius of the circle. We take the radius of the circle as small letter r. We have the meniscus also having a radius. What I'm trying to say is that, when we draw a tangent line between the what? The tangent line that is drawn at between the angle of contact of the meniscus. At the angle of the contact is the angle that makes the tangent and that of the particular solid. Why am I bringing a circle? Let me keep it simple. The reason why I'm bringing a circle is because I want to introduce an angle of contact, as we have already studied in the previous lesson or in the previous slide. Now, angle of contact is angle between the tangent angle between the point of contact and the what? And that of the what? The layers of the what? Cohesive or whatever you call it. Now, here directly, because of time, we still have illustration. In fact, I'm being given a good eye by my people here that I should stop this class. And please, I want to stop. It's just because of explanation that has caused me a lot of reaped me a lot of havoc. So now directly, I know I can show you angle of contact. You remember from what we have studied. Wow, what is going on here? I think even my writing materials are tired. Now, angle between this, you remember, between this and this tangent, which is our theta. Theta here will correspond to theta here. You can form your shape and have something like this. We have big R, we have small r, and we have an angle of theta. What I'm trying to say is that the radius of the sphere is small letter r. And you can give that as a, or let's do it like this. The radius is equals to, we have r equals to big R. What is opposite over hypotenuse? That is what is adjacent over hypotenuse? That is cos theta divided by cos theta. I just want to do that directly. So substituting this value, that is what I just want to bring. You know why I'm bringing this, my dear student? Because when angle of contact is given in the formula, and some of you will be looking like a control human being, should be big R. Sorry about that. Is equals to what? Small r divided by cos theta. So what happened to the formula you have for the height of what this is equals to, what do you have, guys? 2t. What does t stand for? Surface tension divided by p multiplied by g multiplied by, what is your big R? Your big R here is now small r divided by cos theta. Let me show you in step. On the normal day, I know the formula by heart, but I'm just trying to show you in step. Now cos theta will come up. You say, ow. Yeah, let's cross multiply. Should be, cross multiply. Now you can say h, which is the height of capillary 2, is now equals to, let's reduce this first, 2 times surface tension. We are dividing r, g, small r, also divided by cos theta. I hope students can see this. Is this r or rho? This is rho or p. Is it rho or p? We are talking about rho. Rho is the density. So this is rho, please. That's something about me sometimes, the way I write stuff. And that now we can say it's the same thing as h equals to, I'm taking it step, and that is my way. We don't need to rush. 2t all over rho gr times, this is divided. It will now be times, it will have been divided by this, divided by cos this. It will now be 1 over, oh, sorry, this is divided by cos of this. It will be coming up. So I have cos what? Cos theta. I hope you understand it. And if you have issues, please let me know. We're having 2t divided by r, say r, rho gr over cos theta. What I have done is I have just turned this one to multiplication. And when you turn that one to multiplication, what happened will be what you are seeing here. So what I want to write as the final formula here, permits me to clean all this. Or basically, if you know you have issues with this final formula, when you know this one, know that big R equals to small r over cos theta. So if you want to get big R and you are given the meniscus angle, you can directly substitute the value. So my point here is that we can just take it directly like this and say the value of our h is equals to this. If you write it like this, you are good. But if you know that what big R is also equals to small r over cos theta, then if somebody give you, what does small r stands for? The radius of the sphere. What does big R stand for? The radius of the what? The meniscus. Do you understand? So we need to keep this in mind not to make mistake. And this is where I'm going to stop capillarity for now. The rest of the capillarity calculation with respect to our kinetic theory of gas, you can watch kinetic theory of gas video as you are going to see some other further calculation and numerical. on that. And to end this class, we are going to look at some illustration that was set by our student, and let's see how far they were able to see questions on the surface tension. And doing that, let's go to the last slide, which is slide 30. Now, about slide 30, we have, I think we have, oh, we have 4 questions here. There's still one more slide. Fine. Now, a piece of wire gauze, I will be quick about this because time is is fast spent. A piece of wire gauze can be made to lie on surface of water because that we've talked about surface tension. Wire gauze will act like a stretch elastic elastic string or elastic membrane. So the reason is because the surface of water has the effect of an elastic thin skin, and that is what we call surface tension. That's the answer. The next question is which of the following statement is or are true? We have multiple choice question. It says soap powder poured into water increases surface tension. This is absolutely jargons. Why is it jargons? Impurities lowers surface tension. We move. Oil poured into water reduces its surface tension. Oil might not be an impurity. As we've talked about, we have 2 types of impurity. We have soluble impurity, we have insoluble impurity. So you need to be careful about this. This is still wrong. You can't say oil will reduce the surface tension because when you look at oil, what happened to oil when you put oil on top of water? It will stay on top, right? So, and it should It should actually reduce. We should keep that at the back of our mind. But one thing about oil is that you can also use oil to break intermolecular force. You blend that in fission. So you need to understand one thing about physics. So technical question, you just need to be careful. Oil should reduce surface tension normally because oil will stay on top, and intermolecular force will be broken. So if oil is reducing surface intermolecular force, this should be correct. Well, I told you about soluble. So part of the oil might go down and mix with the water, and because of that, we might say it can increase or decrease, and that is why I'm wrong in this one. I know the option we carry this one to be correct, but I need to tell you why most technical questions like this, you have to be careful. And the third one says, surface tension helps to keep the egg of the water. Of course. Why? Surface tension helps to keep the eggs of water. To keep eggs of water. That grammar, I don't understand. But what I think it should have been, what is there? Eggs of water. So that is, surface tension allow what? You understand? It's allowed, it's only occur at the surface. So, and it allow it to egg to stay on top of water because it will, the force will now allow that particular thing to act like a stretch elastic. What I'm saying is that this is correct. Any force that acts on the surface of a liquid or fluid is called surface tension, with respect to an hypothetical. So the answer to that one is 3. 3 only is correct. You can see 2 and 3 is also there for some of you that you are pig-headed and you don't know concept very well. So that is the answer to that. And that's the C and C is the answer. We go to the next slide. Oh, wow. The next slide is also non-numerical. So I'm very, very happy. Thank God about this. Now, by which of the following process does a piece of blotting paper absorb a drop of ink from a thin sheet of writing paper? Oh my God. Now we've talked about, this is junior classes. You know, when we explain the concept of capillarity, I might not give you an example, but I believe you have learned that from your junior classes. A very good example is that you dig something inside water, it will soak. Why will it soak? Because what? There is the capillary rise in the liquid. And again, you know, I was rushing in my explanation to the other one. When we consider the second situation, the second meniscus, it is still the same formula for the height. But the height of the capillary action will not be what? Going up. It will be what? Going down. And because it is going down, the only thing that changes in the formula is what you put negative. I hope students are hearing it. That's why you need to watch all the video to understand the concepts. So I don't need to start deriving again because I'll still get the same formula. But now in this time, it will be negative because the height is going down for a convex meniscus. That is the other one in case of mercury. I hope students get that. Now directly here, when you put which of the following processes does a piece of blotting paper absorb a drop of ink from a thin sheet of writing paper? You are putting, you know that now when you are small, you put ink on top of paper. What happened to the paper? It will be soaked with it. What happened? Capillary action. So that is that. Let's read. The action of force of cohesion between the molecule of blotting paper. That is not, cohesion is not responsible for that only. The action of forces of cohesion between the blotting paper is not the cohesion alone. The capillary rise in the ink into the blotting fiber. Capillary action, valid. The diffusion, not be diffusion, it's not diffusion. The action of the force of viscosity, and this is not viscosity. Viscosity is what? Frictional force in liquid. We've learned that before. Last but not least, two capillary tubes of the same ball are dipped into water. Let's talk about just like the image we use in our explanation. Open. And mercury in water and mercury. So the water rises in one tube while the mercury level falls. That was the exact diagram we did in concept class. We've talked about what concave and convex meniscus. And you know about that. Concave meniscus means what? When something right, we've talked about that theta is less than 90, and that is adhesive force is greater than what? Cohesive force. Now look at this. Now the question says two capillaries of the same ball are dipped into water, and the mercury and mercury respectively. The water level rises into one thing while the other metal falls. This is because dash mercury is denser than, you can't pick density here now. You know the concept we are talking about is not density. Next is that the adhesive force between water and glass is greater than the cohesive force between whatever water. Adhesive force between water and glass is greater than cohesive force. Look at it. We are comparing two capillary tubes. One contains water and the other contains mercury. Let's break it down. And the water level rises in one, and what? It drops in one. We know that the reason for this is that the molecule have stronger bonding. We are not talking about bonding. Adhesive force between mercury is greater than the cohesive force of mercury. Well, look at this. The adhesive force between water and glass is greater than the cohesive force of water. The cohesive force of water is equal to the adhesive force between water and glass. This is valid. Yes, I like this question because you want you to think. Now, look at this statement. The cohesive force of water is equal to the adhesive force between water and glass. Now, for water to go up, like what we've talked in capillary action, we've talked about height above. What happened is because the moment you drop a narrow tube into the water, the meniscus is what actually causes it. Concave meniscus means adhesive force. Let me quickly recall. Is greater than what? Cohesive force. And that is why you see in concave meniscus that what? Water level will rise. So this is what we need. That is why water is going up. And in the other case, whereby the direction of fluid is other way, it will be opposite of this. So you just need to see, look at it, the adhesive force between water and glass is greater than the cohesive force of what? Water. This is what? Valid. Whereas they are not what? Equal. And look at it, the adhesive force between mercury and glass, mercury and glass. Mercury has a low adhesive force. That is why it is what? Going down. It is for mercury to what? To have convex meniscus. What that means, we've learned that is that what? The cohesive force, are you still there? The cohesive force is greater than the what? Adhesive force. So be careful about that. It's what we have learned before. I just want you to what? Understand it. And this is wrong. What the examiner is asking here is that it's just like saying, rephrasing, why does water wet glass? So like I said, the adhesive force of mercury and glass is greater is wrong, as we have already studied before. So not to waste our time, the answer to the question is choice B here. B is correct, as mercury will not wet glass, that's convex meniscus. By water will wet glass, that is concave meniscus, and that is why we are picking B. So that is where I'm going to stop, my dear student. I will see you guys soon in my future video on physics. Don't forget, invite a friend, share the link, and do kindly subscribe to the channel. Bye for now. Do have a wonderful day.